let's do this screencast on activation energy and enzymes. Okay? All right, so a couple things we need to review about from your physical science and probably even back as far as your middle school time. What's chemical reaction and what are the reactants in the products? Well, chemical reaction is when one or more reactants, which is here on the left side of the arrow, chemically react to form a new product here on the right-hand side of the chemical reaction on this arrow. Okay, so that is a chemical reaction. This is the chemical formulas showing the different compounds. You've got carbon dioxide combining with water to become H2CO3, okay, which is carbonic acid. All right, bond energy. Let's talk about bond energy. Well, bond energy as a vocabulary word is just referring to the amount of energy that it takes to break a bond. So when these molecules are broken apart so that they can reconfigure and become this new product, that requires energy. That's what bond energy is. Okay, and a chemical reaction is in equilibrium if this side, the reactant side, energy is equal to the amount of energy that is put out on the product side. So that is what it's meant by equilibrium. Okay, taking that one step further, let's look at another vocabulary word, which is activation energy, probably a new word. But this is the amount of energy that it takes in order to make a chemical reaction go. Okay, so I've got my reactants that are going in. You can see the energy is going up on this timeline. So as the reaction progresses, nothing happens. All of a sudden we start putting in some kind of energy source, and as the energy goes up, the reaction continues, and then eventually the reaction will progress on this side of the graph, as you'll see in the next part. Okay. But activation energy, just as this illustration depicts, is the amount of work that it's going to take in order for that chemical reaction to go. Hence this guy, how much work does it take for him to push this ball up this hill? It's the same analogy as how much activation energy it takes for a chemical reaction to go. All right. Then let's talk about two words that hopefully are familiar to you, endothermic reactions and exothermic reactions. Endo as a prefix means in, right, and thermic is referring to heat. So what we're talking about here is we're talking about chemical reactions that actually absorb chemical energy, okay? So endo means the energy is put in to the chemical reaction. It stays within, okay? If you look at it graphically, you can see here's our amount of energy that we're using. This is our activation. How much energy does it take to make this chemical reaction go? Okay. Then the chemical reaction goes, and in this case, this is what's totally released. And you can see this is the energy that is released, and this is the amount of energy that is absorbed into the products that are produced. Okay. So this is the line of the chemical reaction. This is what was released, and this is what is absorbed into the products of that chemical reaction. And an example of an endothermic reaction is if you're out on the playing field and somebody gets hurt, somebody grabs one of those ice packs, pops it, and then a couple of moments later, after you kind of knead it a little bit, the ice pack feels ice cold. Okay, that's an endothermic reaction. The chemicals inside the packet go through a chemical reaction, and energy is absorbed back into the chemical reaction, and it feels cold to the touch. Okay. On the flip side of that, then you also have an exothermic reaction where energy is released in a chemical reaction. Okay. So here you have your reactants going in. Here's your activation energy. How much energy does it take to make the chemical reaction go? And then you can see in this case the chemical reaction is actually below the baseline. So this is the amount of energy that is released. Okay. So that's why it feels hot to the touch. Okay. Example of that would be like if you get those toasty toes or hot fingers or whatever they're called, where in the wintertime if you open up the package and immediately expose the little cloth pad to air, it starts to activate, and then a moment later it feels warm in your hands. You can stick them in your toes, or you can stick them in your mittens, and so when you're skiing or hunting or playing in the snow or whatever, when it's cold, it keeps it's making heat, so it keeps your hands and your toes warm. That's an example of an exothermic reaction. Remember, exo as a prefix means out, exit, okay, and thermic again is referring to heat. All right, so that's good review from physical science, but definitely stuff that you need to know. Next, we want to talk about enzymes, okay? Well, enzymes are catalysts. That's what they are. And a catalyst, by definition, is a substance that just speeds up a chemical reaction, makes the rate of the chemical reaction go faster. Okay, so it increases the rate of the chemical reaction, and it does that because it decreases the activation energy. So enzymes make it go faster, by decreasing the amount of activation energy. You don't have to put as much effort into it in order for the reaction to go. So I've got my two reactions here graphically. The solid line is what the normal reaction would look like. Okay, you see I put in, and then this is what comes out. Okay, if I add a catalyst, okay, and maybe it's an enzyme to the chemical reaction, you can see that the dotted line has significantly changed how much activation energy has to go in. Here was my initial activation energy, a lot more. Here is my new activation energy. It doesn't require nearly as much energy. Okay, so that's the products coming out. Okay. So that's what we're looking at when we talk about a catalyst. Well, in the human body, the most common catalyst would be the enzyme. Okay. You have lots of them in your body, and they work on lots of different chemical reactions. Most enzymes, and we learned this in our, earlier in this unit when we were looking at our macromolecules, are proteins. Okay, like we looked at helicase, we looked at catalase, we looked at lactase. So all those enzymes are proteins by structure. Okay. Then, we kind of have touched on this concept of homeostasis, but it's the state where your body maintains the same throughout. Okay, that's what homeostasis is referring to. So your body maintains a stability in it. And you know when your body's in homeostasis, and you know when your body's not, because you're not feeling good. Okay, so you might have a fever, you might have chills. That's your body temperature has changed, so you're not in homeostasis. You don't feel good, and that because the thermometer says either you've got a fever, you're above 98.6, or maybe you spent too much time outside and you're getting hypothermic and your body temperature has dropped. Okay, both of those are extremely hazardous when you're not in that state of homeostasis. Okay. Your body also has a very specific pH that it must maintain as well. It's somewhere around that 6 to 7 window in the pH scale. When your body is not balanced like that, it throws your body off whack, and you usually get sick. So either too high of a pH or too low, too basic or too acidic. Okay. So what do these enzymes have to do with homeostasis? Well, enzymes have a very specific range with which they will work in. If you take them outside of that range, they will not function as well. Okay. For instance, you have enzymes that help with your digestive process, right? Okay. When you're sick and you've got a high fever, your body is not going to digest its food as well because those enzymes are not helping out with the digestive process, and you see that by what might be taking place in the bathroom. Okay. So that's what I'm talking about when they have a very specific range of what they will work within. And that includes both temperature and pH. And we're going to do a lab tomorrow that kind of points that out to you. How does temperature affect the functionality of an enzyme? The last two slides basically are talking about the anatomy of how an enzyme binds with a substrate. So a couple pieces here. You've got your substrates, where they hook up at the site of the enzyme. That's called the active site. Okay. If I flip to the last slide, I think it gives a little bit more detail. You can see that, and this whole picture is monitoring the lock and key model. So what happens in lock and key is very specific keys fit with very specific locks, right? I can't put my door lock or my door key in your lock at your home and open your door. It wouldn't work. Only my door key will work on my door at home. And that's what they're kind of talking about here. So an enzyme will work with only very specific substrates. And how that works is the substrates would come in, bind at the active site, chemical reaction takes place, and then the product is released from the enzyme, and this enzyme goes off to do more work. Okay, so it's completely unchanged or unaltered in the whole chemical process. Another way of thinking of this is like puzzle pieces. Very specific puzzle pieces have to fit together, like the innies and the outies on a puzzle. You can't just put any old outie in an innie on a puzzle and expect the puzzle to work. It's got to be a very specific piece. So that is the lock and key model in a nutshell. All right, so keep your notes, bring them to class tomorrow. We're going to have a small little note quiz, open notes, so anything you write by hand is free to use when we take these notes. And I will see you in class tomorrow. Okay, have a great day, everybody.